Hi everyone, and welcome to Adventures in Science. In this DVD I'm going to be showing you how to do 8 very simple science experiments that you can do in the home. All the chemicals and equipment that you need you should be able to find in the kitchen, and you will not require any sort of special expertise to do any of the demonstrations I'm going to show you. Some of them, however, do use fire and hot water, so all I would say to you is be careful, be safe, but have fun along the way, okay? There will be more DVDs in future which will detail some of the more exciting projects, so look out for those. But in the meantime, have fun and let's get experimenting. We're going to start with a very simple experiment, and this one is called the ice lift. And basically what we're going to do is we are going to lift some ice cubes or pieces of ice out of a bowl of water just using a piece of string and some salt. So all you need for this experiment is some ice cubes or some broken up pieces of ice, a bowl of water, preferably cold water, and some cotton, string and table salt. And all I'm going to do first of all is I'm going to put some of the salt, some of the ice cubes into the water, like so, as much as you like. And the next thing you need to do is wet the string. Okay, so I just drop the string in the water, just run it through my fingers like that, and then lay it on the top of as many of the ice cubes as will fit, or as this string will allow. Okay, like that. And then take the salt and sprinkle a little bit, not too much. Again, experiment with various quantities, but just a little bit, just enough to smother the string and cover the ice along the length of the string. And we need to leave that for about half a minute to a minute. So you might want to sing a song or go and do something else while we're waiting for that to get ready. Okay, so we've let that settle and let's see what happens. So take hold of the end of the string and gently lift the string out of the water, and you should find hopefully that a good amount of the ice will come out with the string. So how does it work? Well, the normal freezing point of water is 0 degrees centigrade. If we add salt to water, we can depress the freezing point by several degrees. Okay, so what's happening at the moment is because the ice is floating in water, the ice is slowly melting. And when I tip the salt on top of the ice cubes, this allows the water temperature to go below 0 degrees without actually freezing, because the ice itself has come out of the freezer and the temperature of the ice is actually much lower than 0 degrees centigrade. So we have some already liquid water on the surface of the ice and the wet string. When we add the salt, that enables the temperature of the water to go down much below 0 degrees centigrade. What then happens is, of course, as the ice continues to melt, it turns to water, the water dissolves the salt, and the salt, now the solution, becomes less and less concentrated. And so what then happens is the freezing point of the water starts to come back up to closer to 0 degrees centigrade, and because the ice cubes are much colder than that, then the water then refreezes. And we now have a situation where the water that was sitting on the ice cubes now turns back into ice, but because the string is now actually in the water which has frozen, the string is now trapped inside the ice which has frozen onto the ice cubes, and when we lift up the string we can pull the ice cubes out of the water all in one go without them falling off. And that's basically what's happening. This one is the balloon in the jar experiment, and basically what we are going to do now is we have a water-filled balloon and an old pickled onion jar, and the object of the exercise is to get the balloon into the jar without actually touching it. And this experiment uses atmospheric pressure to do the job. So all you need is an ordinary party balloon fill it with water and just make sure it's big enough so that it doesn't actually fit into the jar through the lid, through the neck, like that. Okay. The only other thing you need is some paper and a lighter, and tear off a strip of paper, fold it up into a spill so that it will actually sort of fit into the jar. And now we'll take the balloon and just put that to one side for the moment. Get the paper, light the paper, get the paper lit. Stay there. So we need to get the paper burning really well to start with. Make sure the paper is burning quite nicely. And then when you've got a good flame, drop it in the jar and then put the balloon on top straight away. The balloon will bounce around on top, and then, hey presto, the balloon will be drawn into the jar like so. Now, there's a lot of misunderstanding about how this experiment actually works. Some people use the explanation that the flame or the burning paper burns up the oxygen inside the jar, and because the oxygen is used up, that's what causes the balloon to be drawn into the jar. But if you think about it logically, the paper is burning up the oxygen, but the oxygen is being replaced by carbon dioxide and smoke. So on balance, there isn't actually any change in the volume of gas. What is actually happening is the air inside the jar is being heated. Okay, there's a flame inside there, and that's why we see the balloon bouncing around on the top of the jar. That is because hot air is expanding and is being forced out past the balloon. However, eventually the fire goes out because we run out of oxygen, it stops burning, and then the gas starts to cool down. The balloon, however, has sealed the top of the jar. The gas inside cools down, the pressure drops, and it is the atmospheric pressure outside the jar which then forces the balloon down through the neck of the bottle into the jar like so. So there is a demonstration about the effects of atmospheric pressure. This next experiment is a very simple one. It's one of a number of experiments basically to demonstrate Bernoulli's principle. And what you will have is a bendy straw which you need to open out and bend into a right angle like so, and a small polystyrene ball, and you just make a ring with your thumb or forefinger, balance the ball on top, place the straw underneath the ball and blow gently, and with any luck the ball should rise in the air and float on top of the straw like this. And as long as you can keep a fairly steady stream of air, the ball should stay there. If you're careful with it, you can move around and walk about, although you may find it's rather tricky to actually get the ball to stay there. And you can experiment with maybe moving the straw from side to side, see if you can get the ball to float side to side and see how far you can get it to move. But this is basically a very, very simple demonstration of Bernoulli's principle, of which we do a load of other experiments at other shows. Okay. This experiment is called the expanding hand, and all you need for this is a few chemicals that you will find in the kitchen. I have here some white vinegar. You can use any vinegar, but I just happen to have white vinegar here. Bicarbonate of soda, sodium bicarbonate, an empty glass jar of that sort of size will do, an elastic band, and an old rubber glove. And the first thing I'm going to do is I'm going to take some of the bicarbonate of soda and I'm going to tip it into the fingers of the glove. You only need to fill about half full the fingers, but again you can experiment with the amount of bicarbonate of powder that you actually need. So squash that in there, get that down into the fingers of the glove like so. And we then take the vinegar, and I'm going to tip about a couple of centimetres of vinegar into the bottom of the jar like so. Again, you can experiment with the quantities to get different effects. And now the tricky bit. We're going to seal the glove over the top of the jar. Now you need to make sure that you don't tip any of the bicarbonate into the vinegar, otherwise then the experiment will start off rather sooner than you want it to. So we'll get the glove over the top of the jar and then seal it in place with the elastic band. Again, this is where you need to be a little bit careful that you don't inadvertently tip any of the bicarbonate into the jar. So we'll get that secured like so, and then when you're ready, all you need to do is lift up the glove, allow the bicarbonate to fall into the vinegar, and you can watch what happens. So we'll tip that into there, and then we can let go of the glove, and you can see that the glove will now start to fill up with carbon dioxide and expand itself. And as long as the reaction is taking place, there will be enough CO2 being given off to keep the glove inflated. The reaction will eventually stop, and then the glove will deflate itself slowly. If you get a nice good seal around the top of the jar, then the glove will stay up possibly for several minutes. But this is just a demonstration as to how the experiment works. Okay, so what's actually happening? Well, basically the vinegar is an acid, acetic acid, and the bicarbonate of soda is actually sodium bicarbonate. And when we mix the two together, the standard reaction is acid plus carbonate gives a salt. In this case it's going to be sodium acetate, plus carbon dioxide, which is the gas given off, and water as a byproduct. And so the fact that we are producing quite a large quantity of carbon dioxide, this is the gas that we use to inflate the glove. And so a very, very simple experiment you can do, but all sorts of applications, and I'll leave it to your imagination as to what you want to do. It doesn't have to be a glove, it can be anything that you want to sort of stick on top of a jar or a plastic bottle. Okay. This one is the classic Cartesian diver. It can be a little bit fiddly, so you do need a little bit of patience in order to make this work, but when it works, it does actually work rather well. All you need for this, if you have the Adventures in Science kit, then you will have one of these little pipettes and a steel nut in the end already made. If you don't, then you can use something like a little eyedropper or something of that nature. Okay. All you really need is the diver itself, a cup of water, and a large drinks bottle, 1 litre or 2 litre bottle, filled to the brim with water. Now the tricky bit is to get the diver into such a state that it only just floats in water. So what you need to do is fill it with water, and just by squeezing it, and drop it into a cup first of all. This is by far the easiest way of doing it. So I'm going to fill this thing with water, and you need to fiddle with it so that it just floats. So I've got to get quite a bit of water in there. Let's pop that, okay, and that's probably a little bit too much, so a little bit more water, and that's a little bit too much. So now once it's sunk, we can now just let out a few drops at a time until it just starts to float. So this is where you do need to take a little bit of time and care just to get it just floating, and that's just a little bit more than that. The amount of which it floats will determine the sensitivity, and that's probably gone a little bit the other way. You can see this is a little bit of a fiddle. So I'll just get a few more bubbles of air out, and then we'll see how that goes. Right, let's try that. And now, without squeezing it, take the diver out and drop it into the bottle like that. Okay, and then put the lid on, screw the lid down, and now you should find that if you squeeze the bottle gently, the diver will start to sink. So I'll squeeze the bottle. I've got to squeeze this quite firmly, yes, okay, and then it will start to go down, sink all the way to the bottom, and if I then squeeze it enough, I can get it to hover part below the bottle, and then if I let the pressure off, I can get it to go all the way back up like that. Okay, so squeeze the bottle and he goes down, squeeze it all the way hard, he goes right to the bottom, and if I get the pressure just right, I can make it float virtually anywhere in the bottle that I choose to, simply by adjusting the pressure on the side of the bottle, like that. Okay, so it's a little bit tricky to get going, as you can see, but once you've got the bubble about the right size, it's actually quite effective. So what's actually going on? Well, inside the little diver, as you can see, we have water and a bubble of air at the top, which you can see. And what we've basically done is we've got just enough air in the diver as it stands to allow it to float. So he's buoyant and he will float in water. But what happens when I squeeze the bottle is I start to compress the water. Well, water is a fluid, fluids are generally incompressible. So what happens is water gets pushed up inside the diver and it compresses the air bubble inside. So the air bubble gets smaller, more water is forced into the diver itself, the mass of the diver, the weight of the diver goes up, he gets heavier, and therefore he now becomes so heavy that he sinks in water. Okay, and he'll sink all the way to the bottom. And if I let go, then the air expands, the bubble gets bigger, it pushes water out, it gets lighter, and he's able to float. And I can get it to float anywhere in the bottle simply by ensuring that the volume of the bubble inside causes sufficient buoyancy for the diver to actually stay in position anywhere where I want to. And that's basically the principle that submarines sort of work on. So there we have a neat little trick, the Cartesian diver. Well, no series of science experiments would be complete unless it involved making a mess somewhere. So here's a quick way of making a simulated volcano. Once you've got the basic principle, you can scale it up as much as you like, but I would suggest that you do it somewhere where it doesn't matter if you make a mess. I'm basically going to do this on a plastic sheet to make it easier to clear up, but you'll find out why in just a moment. Now, once again, we need our old friends, the bicarbonate of soda, some vinegar, and this time we're also going to need some washing up liquid. Okay, standard sort of washing up liquid type stuff, and this is in order to produce foam, and this is really the key to the whole thing. I'm going to use a small plastic, it's an old honey jar, it's got a narrow neck which tends to make the effect slightly better, so you can experiment with different types of container. So the first thing I'm going to do is I'm going to put a few spoonfuls of bicarbonate of soda into the bottom of the honey pot. And again, you can experiment with the amount that you need, but I'm just going to put a couple of spoonfuls in just so that you can see the effect and see how it works. See what happens. Put that in there like that. Okay. Now, the next thing is a good idea to pre-mix the vinegar and the washing up liquid. So I'm just going to put a little bit of washing up liquid in the bottom of this cup, like that, and I'll pour some vinegar in and mix it round, and not too much like that, that should do us. And on the plastic honey jar, I've taken the lid and I've cut out the little soft rubber hole in the middle, so it leaves a relatively narrow hole in the top. So I'm going to screw that on top there like that. And now I'm going to pour the contents, the vinegar and the washing up liquid into the bicarbonate of soda, and it will produce a lot of carbon dioxide, but also it will produce a lot of foam bubbles. And this is really where the simulated volcano comes in. So I'm just going to very gently pour this in through the lid at the top, and we'll see what happens. I'll pour it in there, okay, and lots of foam is starting to come off, it's expanding as it goes up through the top. And there we have the foam, and it's pouring out of the top. And if you feel so inclined, you could make a little model volcano with papier-mâché, clay or whatever. And you can add food colouring. So if you want to add some red, strong red food colouring, then you can make it look like lava. You can do all sorts of effects like that. Okay, and that will sort of keep going for a few seconds. And again, depending on how much bicarbonate you put in, how much vinegar you put in, etc. You can get a bigger or a lesser effect. So this is something which you can experiment with and play with. There are much larger versions of this which I will detail in other videos. You may have come across something called elephant's toothpaste, which produces a much more spectacular sort of fountain of foam, but that uses different chemicals, and I will explain what those are in another video. Okay, so you can possibly top that up if it starts to run out, and it will keep going, but basically there is the basic idea for a little simulated volcano. For this experiment we are going to make a very simple fire extinguisher, and once again we are going to use our old friends vinegar and baking soda or bicarbonate of soda. So for this we need vinegar, bicarbonate of soda, a small night light or a small candle, and a plastic tray. You can use a metal tray, but I'm going to use a plastic one because then it's easier to see what's actually happening. And what I'm going to do first of all is I'm going to sprinkle a little bit of bicarbonate of soda into the bottom of the tray. Not too much, but just enough to sort of cover the bottom of the tray, like that. I'm going to place the night light in the bottom of the tray, so, and I'm going to light the night light. Now you need to do this where there isn't really too much air movement, because otherwise the carbon dioxide that's going to be created will simply be blown out of the tray. Okay, so we need to make sure that we have a fairly still environment. So I'm going to light the candle first of all, and we'll get that burning. So I'll get that, and we'll get the night light like that. Okay, so we can see this is burning quite happily in the air. And what I'm going to do now is I'm going to take some of the vinegar and I'm going to pour it down the side of the tray. I'm not going to pour it on the candle, okay, you must try and keep the candle dry, and just enough to get the reaction going, and then we'll see what happens to the candle. So I'm going to pour some vinegar around like that, and we can see that the candle goes out. There's a lot of fizzing going on, and just to demonstrate that we do have carbon dioxide, I will try and light the candle. So I'll bring the flame in, and as I bring the lighter even close to the top of the container, you can see that the flame actually goes out, and it almost rolls along the top of the carbon dioxide there, like that, and in there I have absolutely no chance whatsoever. If I take a piece of paper, okay, and I will try and relight the paper, so I'll light the paper, and now my lighter doesn't work at all. And if I put the lighter there, and the flame goes out in the CO2. Now I've blown the CO2 out there, so I'll put a little bit more vinegar in. So you need to be a little bit careful with this. And that's fizzing very, very nicely. I light the candle once again, and I put that in there like that, and the fire goes out. And so we have a good demonstration as to the extinguishing properties of carbon dioxide. Well, this is another experiment which is going to use atmospheric pressure, only this time we are going to use it to crush a drinks can. Now all you need for this is a burner. You can use a cooker ring, a gas ring, anything like that, any source of heat, okay? An empty drinks can, standard size, 300mm, and about a couple of centimetres of water in the bottom. That's all you need. Now I've got this one going before I started just to save a bit of time, but you need to get the water inside the can boiling and make sure that there's plenty of steam coming off the outside of the can. So we can see there's quite a bit of steam coming out. You'll also need a glove, because this thing is going to get quite hot, and you want a little bowl of cold water. And you need to be fairly smart with this, so what I'm going to do is I'm going to take the can off the burner and immediately I'm going to turn it upside down into the cold water and we'll see what happens. So we've got plenty of steam coming off. So here we go, I'll take it off, turn it upside down in the water, bang, I'll turn that burner off like that, and let's have a look and see what happens to the can. Well, it's filled up with water and you can see that it is quite effectively squashed like that. Okay. So how did that happen? Well, if I hold up another can and like this, and I was to say, well, what's in it? A lot of people would probably say, oh, it's empty. But in actual fact, it's not empty. There's no such thing as empty containers, certainly down here at sea level. It's full of air, right? So the container has air inside it. Now, when we put water in the bottom of the can and we heat the water starts to evaporate. And when we get the water boiling, it produces lots and lots of steam. And what the steam does is the steam starts to occupy the volume of the can. And so an awful lot of the air gets pushed out and there's a great deal of water vapour takes its place. So there's a lot of water vapour, very little air inside the can. When we take the can off the burner and turn it upside down into the water causes the steam to condense, and the steam then turns back into water, and that leaves a partial vacuum inside the can, because now there actually really is nothing inside the can. There's a little bit of air, but the vast majority of what was in there was water vapour. All that water vapour condenses, turns back into water, that leaves a partial vacuum, and it is the pressure of the air outside, in other words the atmospheric pressure in this room, which causes the tin can to collapse. So there's a very, very simple experiment that you can do, and I'm sure if you hunt around on YouTube you will find some larger versions where people have done it with 50-gallon oil drums, so you can get some quite spectacular effects with that. But very simple, crushing a can using atmospheric pressure.